Okay, now this video concerns using kinetic data to derive rate laws, and this is a very popular IB type question. You might need your calculator for this, okay? Although there are some things you can actually do in your head because the figures are quite easy. You've already done this in a previous video where we saw NO reacting with hydrogen, and we ended up with a third order reaction. Now these are similar. You can see here that I have this reactant and this reactant. Here are concentrations in 3 experiments. Here are the concentrations in 3 experiments. There are the rates, and you have to work out the rate law, the order, and the actual value of K. So I'll do this one for you here. The important thing is that one of the reactants is remaining the same while the other one is changing. And you can see that this one is doubling. And you can see this is going up approximately 4-fold. Okay, so again, that's doubling, that's going up about 4-fold, which means it must be second order with respect to this reactant here, second order. And here, this reactant is not changing, and this one is halving, and this rate is halving. So it must be first order for this reactant and second order for this one. So the rate law ends up being this here. Okay, you don't actually have to write the 1, but this is showing you what the rate law is. And the order is, of course, 3, because it's 2 plus 1 is 3. And the actual unit of K, and the actual value for K, you can choose any line you like, any experiment you like. You just plug in these values, plug in the rate there, plug in the rate there, and then you end up with your value there. And again, you pause the video and try it yourself, and the answer is, here you go. That should be the answer there, okay? So you can check that, and notice the unit there is for third order, dm6 mole to -2 per minute, okay? Now you can try this one. Again, it's useful because it's not changing there, but it is there, and it's not changing there, but it is there. See if you can work out the orders of the reaction, and therefore the rate law, and therefore the value of K. So pause the video, and I'll just give you the answer now, okay? Okay, so the rate law is this, is third order overall. There you go, 3. And the value of K, choosing any line you like, any of the 4 experiments you like, it should work out to be this value here. All right? Okay? Right. Now this one here, we've got 2 different experiments here. There's only one reactant here, actually. And one reactant, and you can see that the concentration is being changed by this much, and the rate is being changed by this much. Pause the video and see if you can work out the rate law. Okay, and I hope you worked out it was first order with respect to the reactant here. And the second one here, again, there's one reactant, changes from this to this, the rate changes from that to that. Hopefully you can work out what the rate law is. Pause the video, work out the changes. And the rate law works out again to be first order. Okay, it's not always first order when there's one reactant, but in these 2 cases, the 2 cases on the screen, they are first order. Okay? Now this one here, we've got 2 reactants here, 2 reactants, and again, good, not changing there, but it is changing there, and not changing there, but it is there. And you can work out the rate there. For the rate law, please. Pause the video, and then I'll click the screen. Okay, you've paused the video. And yes, it's first order with respect to each, and it's second order overall. Okay, and another one, a quick look at this now. Not changing and changing, and not changing and changing. So that's a nice table to use. Okay, you pause the video, you work out the rate law, and it should work out to be second order for NO and first order for chlorine, so it's third order overall. Okay. Now, what's interesting here is that you can't really use this one here because the temperature is different. Okay, you're stuck with the top. It's like a trick question. You can't really use this data here in this particular experiment, or this particular question rather, because the temperature is changing. So you've only got these top three, and it is not changing there, and it is changing there. Okay, and now we have a problem, don't we? Because we don't have anything staying the same there, and this is going to cause a problem. And this is why I wanted to pause on this one and show you that you have to use rate ratio in this particular example. Okay. However, what you can do is, since you can work out the order for this reactant, that stays the same, that is doubling, and this is doubling. So you know it's first order for A. We know it's first order for A, but we don't have it staying the same there. Nevertheless, we can still work it out like this, because if we look, say, at this experiment here, we are doubling this, and we are changing this to a quarter of what it was. So that's gone down fourfold. And this has doubled, and nothing's happening. There's no change. Now, we already know this is first order, so the fourfold decrease that you should get if it was just this reactant, first order, is being cancelled out by a simple doubling of the concentration here. So really, it could be done mathematically with rate ratio, or you can just put your hands in your pockets and say, look, I know it's first order for this one, and I've gone down fourfold, no change when this one is doubled. And that should tell you that it must be second order for B, okay? So you should end up with this kind of thing. We know, we plug these values in here, in this first one here, and we've got this value here for the next experiment. That's this experiment here. Okay, we've got the numbers here for reactant A. Here are the numbers for reactant B. We know this is first order. We're trying to find that there. And from that, you should be able to work out that the value for X has got to be 2. Okay, now here's an exam. This is an IB exam example where you have to use rate ratio. And the figures are a bit more complicated to use. But there's the reaction. And the rate law is this, and our job is to find out what N and M are. We don't know what those are, and we're given this table. This is from an IB question some years ago. Okay, now initially we can say, oh well, this is good because this is not changing, this is changing, and we can see what's happened to the rate there. Okay, so this one's not changing, this is changing, and this here is changing, and from that we can work out the order with order for ammonia. We can work out the value of N. Okay, and we'll do the whole thing by rate ratio just to prove that this will work. Anyway, this is the expression for the rate law, and this can be called experiment 1. All of that data is going to come from experiment 1, the rate for experiment 1, and this is going to be experiment 2. Okay, and the K's cancel out, and I get this expression now here, and this has stayed the same. This has stayed the same here for this this reactant here. So I can cancel out these like this, and now I'm left with this. The rate for experiment 1 divided by the rate for experiment 2 is this divided by this. I'll just leave out the 10 to the minus 2 because I only want the actual ratio. And I've got here this concentration of ammonia and this concentration down here. It's changed to this one here. Okay, I leave out this because it's the same. And I end up with a value of 1. Now, you didn't really need to go through all that to get that value for 1. That wasn't too difficult to get the value of first order, okay, for the ammonia. But now you can use that now in the next rate ratio calculation. So there's the order with respect to ammonia is 1. And now I'm going to use experiment 4 and divide it by the value for 3. So I'm going to divide this value by this value, and I'm going to put in the values here. Here are the values for the ammonia. Okay, we'll just leave out that again because it's just a ratio. We know that's 1 from our previous calculation. And here are the values that we've got for BF3. Okay, and there's the unknown. And now we just use math and we work out that the value for M turns out to be 1. Okay, it's not chemistry, that's just mathematics. Okay, and so therefore it's first order with respect to each of those reactants and second order overall. Okay, now here's another one where you have to use rate ratio. Stays the same, it changes and changes, so we can work out that one, but there's nothing staying the same there. Okay, so here we go. We're trying to work out what A and B is, and here's the rate expression for experiment number 1, and here's the rate expression for experiment number 2, and we can put the values in. Here we go. Experiment 1, experiment 2, put the values in. These are staying the same. We can cross out all those things. We're left with this here, which we can simplify. Okay, that comes out to be 0.37. I can now simplify that. I can put a bracket around there, get rid of the both A's and just have the 1A, and that turns out to be 1. So it's first order, okay? It's first order with respect to that reactant there, okay? And there we go. We know it's first order now with respect to this one because that was staying the same and that helped us. We didn't really need to do the rate ratio. We could have done it with our hands in our pockets, but we did it anyway. Now we want the value for the reactant B. We want this one here. That's nothing staying the same there, so it's much more difficult. But if we take experiment 2 and experiment 3 and we plug the values in, here we go. We've plugged all the values in. We already know that the value for A is 1, so we can put a bracket around there and put 1, and we can work out this and put a bracket around and put B as the exponent. This ratio comes to 1.38, and then we end up with a value of 1. So it ends up as being first order for each. Now, that was another example where we had to use rate ratio. It was easy to get the order for this one with or without rate ratio because that was staying the same, that was changing, this is changing, and you can actually see its first order. But it was much more difficult to get the order for this because nothing was staying the same there. But we knew the order for this one, and therefore we could work it out using rate ratio. Okay, so I hope that helps you, and I'll do a final video now after this one involving a special reaction with propanone. Okay, that again comes up often in the exams. Okay, thank you.